Hey, what's up everybody? In this section we're going to go over our final problem example for the two pointers pattern, which is another problem from our Leetcode patterns list. This problem can be found by filtering the list like so. In this problem, we're asked to merge two sorted linked lists into one sorted linked list. The problem description also says that the merged list should be made by splicing together the nodes of the first two linked lists, which just means that we aren't going to be creating new list nodes in memory. We're just going to be adjusting the next nodes that each individual node points to such that the final result is a combination of the two original linked lists in ascending order. So what does that actually mean? Well, let's have a look at the diagram that they give us for the first example in the problem description. So these are the two linked lists that we need to merge. Currently, the nodes of each individual linked list have no connection to one another. So we have two linked lists, each containing nodes that are stored in memory. What we want to do is alter these next pointers to merge the lists together in ascending order. So to visualize this, let's just remove all of the next pointers and start from scratch. So now we are just left with nodes in memory which we need to connect in ascending order. So we can start by connecting this node containing the value 1 to the other node containing the value 1, since these are the lowest values. And then we can point the one node's next node to the node containing the value 2, and then to the value 3, and finally the value 3 to 4, and 4 to the other 4. So the end result is a linked list that looks like this. And as you can see, we never created any new nodes in memory. So you can probably guess that the space complexity of the algorithm that we are going to be implementing is O of 1, or constant, because we don't use any additional space. We never create a new node in memory. We just use the nodes that already exist in memory, but more on that later. So the problem that we're trying to solve here is straightforward enough, so let's get into writing some code. Okay, so in our two pointers directory, we want to create another folder that we will call merge two sorted lists. And then we'll just change directory into that folder. And within here, we will go ahead and start up another virtual environment. And let's just go ahead and clear. And now we have our virtual environment folder within our merge sorted list folder, and we can go ahead and activate this virtual environment. And then we want to create a file called merge2sortedlist.py. And then we can go ahead and open that file. And actually the first thing that we want to do is we want to go to the problem. And this problem in particular uses a linked list data structure. If we change this to Python 3, they actually give us the class definition for the node of the linked list. So we can just go ahead and copy that class definition and we can paste it into our code. And let's go ahead and uncomment this. And now we have this class list node, which is going to be what we use to make our linked list. And before we write the algorithm for this problem, let's go ahead and create our entry point. And within this block, we're actually going to need to create the linked lists from the example. Usually the input is something like an array, so we can just copy and paste the array into the input of the function. But here, the input actually needs to be two linked lists. So we actually need to create those data structures using this list node here. And it's quite simple how we do that. So first, let's go ahead and just say our merged list is going to be equal to merge two linked lists. And that's going to take in list 1 and list 2. And we haven't created this function yet, this merge two linked list function, but we're going to. That's going to be where our algorithm is. But we're going to create the linked list that we need to pass in as arguments to this function. So to create the first linked list, we'll do L1, linked list 1 is equal to list node and the value 1. So let's go back to the problem really quick. So the example that we're going to be working with is this one here. And we need to create this linked list, 1, 2, and 4, and this linked list, 1, 3, and 4. So we can go ahead and copy this, and we can just paste it here for reference. We'll comment it out and leave it there for reference. So we're creating the first node, which is essentially the head of linked list 1. So this, we're creating the head of linked list 1. So this is the head of the linked list, and this is the tail of the linked list. And if you're unfamiliar with the linked list data structure, I have an entire series on data structures, which includes the linked list data structure. So if you need to brush up on your data structures, please reference that course. So anyways, here we're creating the head of the linked list. And then we're going to set our head.next equal to a new list node, which contains the value 2. Because our head is this value here, and then the next node from our head is going to be the value 2. And then our tail is going to be 4. So here we're going to set our L1.next equal to 4. And this is going to complete the construction of linked list 1. So now we can do linked list 2, and we'll set it equal to list node, and the first value is also 1. So now we're building this linked list. So the head is 1, the value after the head is 3, and the tail is 4. So we'll do L2.next equals 3, and L2.next.next equals 4. And now we've completed the construction of linked list 2. And we are passing both of them into our merge two linked lists function, which we haven't created yet. And to test this out, once we're finished writing the code for our algorithm, we're going to want to print the linked list to see if we get the correct linked list. So we can write here expected output, and we can go back to our problem and copy this output. And the expected output is this. And we're going to write some code to actually print the linked list, because we can't actually just print merged list like this, because this is just going to print an object. It's not going to show the details of that object. So we actually need to create a node which is equal to merged list. And remember, merged list is a linked list data structure. So merged list is going to be a pointer to the head of our linked list. And merged list.next would be the next value in the linked list. So we're going to set our node that we're working with equal to the head of our merged list. And then we're going to do while node. We'll just print node.value. And then once we print the value, we're going to change node to node.next. So this is how we will move to the next node after printing the value for the current node. And that is how we will print the linked list. So now we can go ahead and start writing this algorithm. So we'll go back to the top of our file here under our class, and we'll define merge to sorted lists. And the parameters will be L1 and L2, of course. And to start this algorithm, we're going to create a placeholder, and we're going to set it equal to list node. And what this essentially is going to do is it's going to allow us to create this linked list without wrapping it in a class. We're just going to use this placeholder empty list node and set its next node to the actual head of our linked list, because we need a way to keep track of where our linked list actually starts. Like, we need a way to access the head of the linked list. And if we don't have this placeholder here, we're going to continue to append values to this linked list and traverse down to the tail of the linked list, but we won't have a way to actually access the beginning of the linked list without traversing backwards. And this is actually a singly linked list, so there's actually no way for us to traverse backwards. That would only be possible with the doubly linked list because the node would have a reference to its previous node, which is not the case in our situation right now. And if this is confusing to you, please just bear with me until we get to the visualization. But also, if this is confusing to you because you don't understand how linked lists work, then I suggest you take the time to watch the video in my data structures series that explains linked lists. So once we create this placeholder node, which is just an empty node, we're going to set the tail of our linked list to placeholder. So currently our tail pointer is going to be pointing to this empty node placeholder. And then we're going to set our L1 pointer equal to L1, which means that our L1 pointer is going to be pointing to the first node of our L1 linked list. And our L2 pointer is going to point to L2, which means that L2 pointer is going to point to the first node of our L2 linked list. And these are the two pointers that we're using for this algorithm, which is where the two pointer technique is being used. We're going to use one pointer for the linked list L1, and we're going to use another pointer for the linked list L2. And we're going to use those two pointers to compare the values in both linked lists. So we'll do while L1 pointer and L2 pointer. So that just means that while the values that the L1 pointer and L2 pointer are pointing to are not null, we're going to compare the two values. So if L1 pointer dot value is less than L2 pointer dot value, we're going to add that node first to our merged linked list. So tail.next equals L1 pointer. So here when we set tail.next equal to L1 pointer, we're setting tail.next equal to the node that L1 pointer is pointing to. And that's going to include all of the subsequent nodes that come after the node that L1 pointer is pointing to. And I know that this is quite confusing, but don't worry, we will do a Blackboard visualization after we write up the code. So then we're going to set our L1 pointer equal to L1 pointer.next. Our L1 pointer will then point to the next node in the L1 linked list. So if L1 pointer.value is not less than L2 pointer.value, then we're just going to set tail.next equal to L2 pointer. And same as before, we will set L2 pointer equal to L2 pointer.next. And finally, we will set our tail equal to tail.next. So we will move our tail up or forward. And lastly, we want to handle the case where both pointers are not non-null. So it's possible that one of the input linked lists is longer than the other. So in that case, while L1 pointer and L2 pointer would resolve to false, but there would still be values left in one of the linked lists. So in that case, we want to check to see if L1 pointer by itself has a value. We'll do tail.next equals L1 pointer. And that will set the end of our linked list to point to the node and the subsequent nodes of L1 pointer. And we can do that because we know that both linked lists are ordered, and if one exceeds the length of the other, then appending the rest of the one that exceeds the length of the other to our merged linked lists will maintain an ordered merged list. And again, if me just explaining this verbally is confusing, don't worry, I will go into a visualization soon. So elif L2 pointer. So if L2 pointer is the one that's not null, then we'll do tail.next equals L2 pointer. And lastly, we're just going to return our placeholder. And remember, we used the placeholder to keep track of where the head of our linked list is. So the head of our linked list is going to be placeholder.next. Because remember, the placeholder is just an empty node. And then let's just go ahead and format. And that's going to be it for the algorithm. And now we should go ahead and test this. And we have an issue here. It says merge two linked lists. And the name of our function is merge two sorted lists. Sorry about that. So this should be merge two linked lists. Actually, the problem is called merge two sorted lists. So this should be merge two sorted lists. And so should this. And let's check to see if we have merge two linked lists. And we don't. Okay, so now we can go ahead and save this, and we can go ahead and run this file. And the linked list that we're getting printed is 1, 1, 2, 3, 4, 4. So let's check the output of the problem example. And the problem example expects 1, 1, 2, 3, 4, 4, which are the same values contained within the linked list that we just printed, 1, 1, 2, 3, 4, 4. So now let's get into the visualization for this code. Okay, so let's take some time to attempt to visualize this code. And let's start by going over this class ListNode. So this ListNode class is just the class for a node in a linked list. So a linked list is going to be a list of these nodes. So for example, we could have list node, which we will just represent by this square. And it will have a next pointer and some data. And actually the data would be this value variable here. So we'll just put val here, and this represents our next. And to create a linked list, a singly linked list, as you can see here, a singly linked list, we would just continue to add nodes to the list. And the reason it's a singly linked list is because we only have next pointers. We only can go from the head of the linked list to the end. We only can go in that one direction. A doubly linked list would mean that the nodes also have a reference to their previous node, so we'd be able to go forward and backward. But in our case, with this singly linked list, we can only go forward. So whenever we're creating a new node and we're creating another node using node.next equals, we're essentially just adding a node to our linked list. So this is what I want you to visualize as we're going through this problem. So let's go ahead and erase this for now. And let's have a look at the beginning of our function here. So the first thing that we're doing here is we're creating a placeholder, which is just an empty node. And we're just doing this so that we can keep track of where our linked list actually starts, because we're not wrapping these nodes in a linked list class. So our merged linked list is just going to start off with an empty node that points to none. So this here is this placeholder node, this empty node. And the reason it points to none is because if we create a node, a list node, the default value for its next is none. So the next for this empty node is going to be none. And then we're going to set our tail equal to the placeholder. So we can just write here, tail. And now as we traverse down this linked list and continue to add new nodes, as we merge the two input linked lists, we'll always have a reference to the beginning of that linked list, which is beneficial because this is a singly linked list, so we can only go forward. There's actually no way for us to backtrack to the beginning node. So the way that we're going to access the first node is by referencing this placeholder node's next node. And you're going to see what I mean by that soon. So to start, we're going to set our L1 pointer and our L2 pointer. So these two pointers here are what make this an implementation or use of the two-pointer technique, because we're going to have one pointer that points to a node in our first linked list and one pointer that points to a node in our second linked list. And we're going to compare those values to see which one should go first in our merged linked list, because the goal of this whole algorithm is to merge two ordered linked lists into one ordered linked list, ordered or sorted in ascending order. So let's go ahead and take our input into consideration here. So the input for the problem is going to be two linked lists, and those two linked lists are going to have the values 1, 2, and 4, and 1, 3, and 4. And I know that the way I wrote these looks like they're arrays, but I'm just writing that so you can see the values for the input. And that's the way that it shows in the actual problem example as well, but these are actually linked lists. So actually, let's go ahead and write out each linked list as it actually looks. So this one is L1 and this one is L2. So we'll go ahead and create L1. And the values are 1, 2, and 4. And this is the head, and this is the tail. And let's also create L2. Actually, we can do L2 in a different color. So we'll do L2 in green. And this is the head, and this is the tail. And the values are 1, 3, and 4. So these are the two linked lists that we want to combine into this merged linked list here. And let's write out our pointers as well. So we're setting L1 pointer equal to L1, and this is a linked list data structure. So L1 is going to be the first node of the L1 linked list. It's not going to be the entire linked list. It's just going to reference the first node. And to access subsequent nodes, we need to do L1.next and then L1.next.next, etc., etc. So that's why we're setting the pointer equal to L1. It's setting this pointer equal to the first node in this L1 linked list. So we'll say L1 pointer is pointing to the head of the L1 linked list. And the same thing with L2 pointer. It's pointing to the head of the L2 linked list. So once we've set up our pointers, we can go ahead and start this while loop here, which is first going to check if the L1 and L2 pointers are pointing to nodes that aren't null or none. So for this while loop to continue, both the L1 pointer and the L2 pointer need to be pointing to nodes that have values. And in this case, both of these nodes have values. So we'll move down to this line of code, which then asks which one has the smaller value, because whichever one has the smaller value needs to go into our merge linked list first, because this is an ascending order linked list. So it checks if the value at L1 is less than the value at L2. So the value at L1 is 1 and the value at L2 is 1. So this condition is not true because the value at L1 is not less than the value at L2. They're both the same. So we're just going to go down to this else here and we're going to perform this code. And it actually doesn't matter because they're both 1, but this code is only executed if this top condition is true and if they're the same, or if L1 is greater than L2, then we're going to do this one. So this else is just essentially killing two birds with one stone. We don't need to check to see if both values are equal. So here we will set tail.next equal to our L2 pointer. And remember, our tail is this empty node here currently. So we're going to set this none node equal to our L2 pointer, which will essentially be the first node of our merged linked list, or the head of our merged linked list. So we'll set tail.next equal to the L2 pointer. The L2 pointer points to this node here. So we'll go ahead and erase this none, and we'll create an additional node. Now here things are going to get a bit tricky because we're setting this tail.next node equal to the node that this L2 pointer is pointing to, which is this one. So that means that this tail.next is going to actually reference this same object in memory as this L2 pointer is referencing. So this is essentially the same object as this one, which means that this node's next node is actually this node. Okay, so let's briefly go over what I mean when I say that we are referencing the same node in memory. In order to understand how this algorithm is working, you need to have a general understanding of how variables work in Python. We can think of a Python variable as just a name attached to a particular object. So if we were to write code that looks like this, what that would actually look like in memory is something like this. And if we were to use that same variable to do something like this, what that would actually look like in memory is something like this. So that means that if we were to compare the two variables to see if they are equal, we would actually get true because both x and y point to the same object. This same logic applies to our nodes. If we do something like this, in memory it would look something like this. So for this algorithm in particular, it is important to have at least a general understanding of what is happening under the hood with these variables. So with that in mind, let's continue with our visualization. It really helps to understand how Python variables work with this algorithm in particular because of the way that object referencing works. So let's just continue here. So at this point, this node is going to be referencing this node, which means that this node's next node is going to be referencing this node because this node is pointing to this same object that the L2 pointer is pointing to in memory. But then we're going to arrive at this line, which we're going to change our L2 pointer to point to L2 pointer.next. So L2 pointer.next is this node. So we're going to change this to point to this node. And following that, we're going to set our tail equal to tail.next. So our tail is currently here. We're going to set it to tail.next here. So we can go ahead and erase that. And then we go back up to the top of our while loop again to check to make sure both pointers are pointing to a non-null node. And then once again, we'll go here and we'll compare the two values. So we're going to compare the L1 value to this L2 value. So if L1 pointer.value is less than L2 pointer.value, so L1 pointer.value is 1 and this one's 3, so it is less. So now we're going to do this code. And at this point, we're going to set our tail.next equal to L1 pointer. So our tail.next is no longer going to reference the object here. So we can go ahead and erase that. So this node here is now referencing this node, which means that this next node would actually be this one for now. And just a quick note, as you can see here, we changed this node's next pointer from this one to this one, because remember this one references this same object. So that means the next for this node is the same as the next for this node. And we just set the next for this node to this node here. So actually this node now points to this node as well. But this actually doesn't matter because we're done with this node or this part of the linked list. The part of the linked list that we need to worry about now is this part. So this node is referencing this node, which has a next that points to this node, which means that this node's next is this node as well. And I know that this is terribly confusing, but I really don't know of another way to explain this. So I'll go ahead and write the values in here so it's more clear that this node is this node and this node is this node. So this one is also 1. So we've set tail.next to point to the L1 pointer value. And now we're going to set our L1 pointer to be equal to L1 pointer.next. So this pointer is now going to point to this one. So we'll erase this and we'll point it to this one. And let's go ahead And let's go ahead and erase this too so we can make some space. So once we've done this, we're going to go back down to here and we're going to set our tail equal to tail.next. Let's erase this as well. So this tail is going to move here. Tail is equal to tail.next. And back to the top of the while loop we go. And we're once again going to check to see if the L1 pointer and L2 pointers are pointing to nodes that have values and that are not none, which is the case. We have this node and this node, so definitely not none. And we'll then compare these again. So now the node that's being pointed to by the L2 pointer is larger than the node being pointed to by the L1 pointer. So once again, we're going to do this code here. So we're going to set tail.next equal to L1 pointer. And technically this tail.next is already pointing to this L1 pointer because remember, this tail is just referencing this node object here is already pointing to this here. So we can go ahead and write that in. And the value is 2. So that means that this node is actually referencing the same node here. And then here we'll set our L1 pointer equal to L1 pointer.next. So we can go ahead and erase this and point it to L1 pointer.next. And then we'll end up here again where we're going to set our tail equal to tail.next. So tail.next. So let's erase. So this is our new tail. And once again, back to the top we go. And this condition resolves to true, so back down to this line. So this value at L1 pointer is greater than this value at L2 pointer. So now we're going to go down here to this code instead. And we're going to set tail.next equal to L2 pointer. So tail.next is going to become this. So this is going to become this. This is pointing to the same object. So we can go ahead and throw a 3 in there. And then we're going to set our L2 pointer to L2 pointer.next. So L2 pointer.next. And currently, of course, since this is pointing to this object here, this has a next, which is this. So we'll go back here and set our tail equal to tail.next once again. So tail.next. So that's our new tail. And then back to the top of the for loop. And this condition resolves to true again. We have a node here and a node here that aren't null. So back to this here once again. And at this point, both of these values are equal. So we're going to go down here and we're going to set tail.next equal to L2 pointer. And technically, this tail's next value is the same as this node's next value because this points to the same object. So technically this already points to L2 pointer, but of course we're going to do it anyway. So that is that for. So tail.next equals the value at L2 pointer. So then we change our L2 pointer to point to L2 pointer.next, which is none. So this will change to point to none. And once again, we end up here where we set our tail equal to tail.next. So tail becomes tail.next. That's our new tail. And back up here we go. So at this point, we have our L1 pointer pointing to a node that's not null, but we have our L2 pointer pointing to a null node or pointing to none. So this condition is actually going to resolve to false, but we still have a value left in this L1 linked list. So we're finished with the L2 linked list, but one of them still has a value that we need to add to our merged linked list. So this code, this while loop finishes. And that's what this code here is for. This code is to handle the case where one of the linked lists we're finished with, the pointers pointing to none, but the other linked list, we still have a value that we need to add to our merged linked list. So in this particular case, it's going to be if L1 pointer. So L1 pointer points to a node that has values, a node that has an object, not none. So if L1 pointer will resolve to true. But the same is for L2 pointer. If the case were that this list was finished and this one wasn't, this condition would be the one that we execute the code within. But in this situation, it's going to be if L1 pointer has an item still, but L2 pointer is pointing to none. So we're going to set tail.next equal to L1 pointer. And the reason we only have to do this once is because we know that these two linked lists are in ascending order. And we know that there's no more values being pointed to in one of the linked lists. So we know that if we set tail.next equal to L1 pointer, it's going to be equal to the object at the L1 pointer. And any subsequent object, so even if this went on for many more nodes, all of them would be added to the end of this merged linked list. Because since this L1 pointer is a reference to this object, and this object has its own next references, we'd essentially take this object and every subsequent object after it in the linked list by just setting tail.next equal to L1 pointer. So let's go ahead and write that. And it points to none because this points to none. We're setting this to reference this same object here. I hope that makes sense. And lastly, let's just go ahead and write the value in there, 4. And here is our merged linked list. And here's our placeholder node. Just go ahead and write placeholder there to prevent confusion. So that means that once we arrive at this line of code, because this is the next line of code that we will arrive at, we're just going to return placeholder.next. And if we return placeholder.next, this next points to this object here. And this object's next value, and this object's next value, and this object's next value can all be accessed by using this next. This next would be the head of the linked list, of our merged linked list. So we only need to return placeholder.next. And our merged linked list would be 1, 1, 2, 3, 4, 4. And as you can see, it's in ascending order. 1, 1, 2, 3, 4, 4. And that is my best effort at explaining how this merged two-sorted linked list algorithm is working. And if you had a particularly difficult time understanding this in particular, I suggest that you make use of some additional resources on linked lists. I also have a series on data structures in Python, so you can also reference the linked list portion of that series as well. So now, last but not least, let's just get into the time and space complexity of this algorithm. So let's go ahead and start with our time complexity. And bear with me here, I'm going to have to make this a little bit smaller. So when taking our time complexity into consideration, we essentially need to take into consideration two separate inputs. We have the list 1 and list 2. And we will have the variable name m equal to the length of list 1, and we'll have the variable n equal to the length of list 2. And our time complexity here is going to be big O of m plus n. And the reason we get big O of m plus n is because in the worst case scenario, our L1 pointer and our L2 pointer are both going to need to touch more or less the entirety of all of the nodes within their corresponding lists. And that's in the worst case, of course, because we can have a case that looks something like this, where we have list 1 and list 2, and list 1 has values like 1, 1, and 2, and list 2 has values like 20, 30, 40. And of course, in a situation like this, we would say within this code block for the entirety of this while loop, so the only pointer that would be moving is this L1 pointer up this list 1. And at the end, we'd arrive at this code here, and we would just append all of list 2 to the end of the list, because all of the values in this list are greater than the greatest value in this list. But that's being optimistic. And in Big O, we want to be pessimist. We want to consider the worst case scenario. So in the worst case, we will need to touch every node within both lists. So for example, in this case, we needed to move both the L1 pointer more or less to the end of the list and the L2 pointer more or less to the end of the list, because we had to keep switching between this if block and this else block. And although we didn't have to touch every single element in both these lists, since we're dealing with Big O, even if we have to touch relatively close to every node within both lists, then we can conclude that the time complexity of this algorithm in particular is O of m plus n. And to make things clear, I'll make this m red because this m is this list here. And I'll make this n green because this n is this list here. And then I'll go ahead and just add a plus in between them. So our time complexity is O of m plus n, where m is our first list and n is our second list. So the time requirements for this function will scale linearly with the size of m plus n. And as for our space requirements, the space complexity is actually going to be O of 1. The space complexity is going to be constant, and that is because essentially all we're doing when we're creating this merged list is moving the pointers around. We're not allocating any new memory. We're just changing the next pointer for the nodes that we already have in these original two lists, but the nodes are actually the same nodes in memory that we start with. For example, this first node here for our merged list, as mentioned before, is referencing this node here, which is the same object in memory that the original head of this list referenced. So we're not creating a new object in memory. We're just pointing our next pointers to objects that already exist within our memory. So we point this placeholder node to this object in memory. So actually this here that I wrote out is just symbolic. Like I wrote this out so that you guys can see that we're creating this merged list to be returned, but this merged list, the nodes contained within it, they're all actually just symbolic because this one actually is just referencing this, and this one is just referencing this, and so on and so forth. So we're actually not using any extra space for this. We're using constant space. So our space complexity is O of 1, and our time complexity is O of m plus n. And again, I understand that this is all quite confusing. Once you become accustomed to the way that pointers and linked lists work, then you'll begin to feel more comfortable with solving and understanding problems like these. But anyways, that's going to be it for this problem. I hope that this information was helpful to somebody, and I'll see you in the next one.